So today we are going to review and look at exponential models and their graphs. Before we start looking at the models, let's take a little review of exponents and their rules. This a at the bottom is called the base, so my bases are the same, and I'm multiplying. And if my bases are the same and I'm multiplying, and I have two different powers, then I can add the powers up. An example of this would be something like 3 to the second times 3 to the fifth would equal 3 to the seventh, because 2 plus 5 is 7. The next rule, my bases again are the same, my powers are different, and because this time I am dividing, you subtract the powers. So an example of this is, let's say, 4 to the sixth over 4 to the third. That's going to be the same thing as 6 minus 3 is 3, so this would be the same thing as 4 to the third. In law number 3, if you have two or more things inside parentheses, this power on the outside has to be given to everything inside the parentheses. Now make a note. This is multiplying. That's why this works. You cannot do this if there's a plus or minus sign in between the things inside the parentheses. So just make sure that you're multiplying. So an example of this would be 2x to the fifth. That would be the same thing as 2 to the fifth, x to the fifth. The next one, same idea as law number 3, except for now we're dividing them, but the top and the bottom have to get that power. So if I had, I don't know, y over 6 to the third, that would equal y to the third over 6 to the third. Little note, b cannot be 0. The thing in the denominator right here cannot be 0 because we can never divide by 0. The next law, if you have a base that already has a power, an exponent, and there's another exponent, you take these two exponents and you multiply them. So x to the third and then raised to the fifth, you multiply the 3 times the 5 and you get x to the 15th. And then the best rule of all, anything to the 0th power, or almost anything to the 0th power, is equal to 1. The only exception to this is 0 to the 0th power is undefined. But anything else to the 0th power will always equal 1. Okay, so now on to our exponential models. Quick note, right here, actually let me grab my, right here, here, and right there. And there, just make sure your notes were not cut off by the copy machine. My version was, but on the screen it looks just fine. So you might have to fill your notes in right there. If you need to do that, go ahead and pause the video and do so. Okay, so the function f of x equals b to the x. The function f of x equals b to the x, where b is greater than 0, or greater than 1, is the parent function for the exponential model, where b is known as my base. The variable x is going to be in the exponent this time, which is why we're studying exponentials. And these graphs don't really have a rate of change anymore. Only lines have a rate of change, but our graphs are going to be either increasing or decreasing, and that will determine whether we are growth or decay. So if my b is greater than 1, it's growth, so bigger than 1, I'm growing. If b is between 0 and 1, I am decaying. So if we look right here, this right here is my b. That b is between 0 and 1, so this graph is a decay graph. So it's getting smaller as time, or whatever the x variable is, goes on. However, in the next example, this right here, that 2 is bigger than 1, which makes this a growth graph, which means as time goes on, I should be getting bigger and bigger and bigger and bigger and bigger. There are many real-life phenomena that can be modeled by exponential models. One of the most famous ones is the spread of diseases. If you think about coronavirus, which we are currently or have most recently dealt with, it goes to one person, that one person can infect more people and then more people and so on. The A in the front of both of these equations, this A right here, this A, my 100 or my 1 is my initial the initial thing I start with, and then this is what I'm doing to it. So in this case, I started with 100 and I'm halving it. This thing I started with 1 and I'm doubling it or multiplying by 2. So at the most basic algebraic level, what happens is we start with some A, initial amount, some A, some initial amount. And then if you want to think about this as a percentage, we start with 1 or 100% plus some R, which is a rate. And then when we add it, it's a growth. In this case, I start with 100%, and if I'm minusing my rate, that means I don't have 100% anymore, which means I'm having less and less and less every time, which makes it a decay. So friendly reminders, A is my initial amount, R is my rate, and X is the number of time intervals that have gone by. So let's take a graphical look at what this looks like. So on my first problem, so I have my model, and it says, I'm going to write above it, make it a little bit bigger. So here is my, okay, so if we look at these, this is my A and then my B to the X power. So my A is 3/2, which is 1.5. That's my initial amount. And the B is 5. Because B is greater than 1, this one's going to be a growth. In number 2, A, B to the X. My A is 2, my B is 1/3. Because 0 is less than B, which is 1/3, which is less than 1, this is going to be a decay graph. We're going to use number 1 and number 2 to sketch the graphs. So number 1 right here, we'll go with number 1, number 2 with number 2. So to graph these, we're going to go back to old school basics. To make a graph, when we first learned how to graph anything, we made a table. So for this one, I'm going to write the equation on here. Y equals 3/2, 5 to the X. So I'm just going to pick some pretty basic things. Let's try X, Y. Let's try -1, 0, 1. So if I do the math for this, if I plug in -1, I get 3/2 times 5 to the negative first. And if you don't remember, if you have a negative exponent, it flips to the bottom. So you have 3/2. It flips it over, so 1/5. And when you multiply fractions, you multiply straight across, so you get 3/10. This is going to be 3/10. For the next one, anything to the 0th power is 1, and then 1 times 3/2 is just 3/2. And then for the last one, 1 as a power makes the 5 just a 5. 5 times 3/2 is 15/2. And if you don't like that, we can change both these. This is 1.5 and this is 7.5. So let's graph these dots. So at -1, I'm at 3/10. I'm very small. At 0, I'm at 1.5. And at 1, I'm at way off my graph up here. So here is my graph. Let's try a similar idea for number 2. I'm going to make my table. X, Y. You don't have to always use these points, but they're pretty basic and small, so that's why I'm using them. So if I do this first one, I get 2 1/3 to the -1. That flips my fraction over, which makes it 2 times 3, or 3/1, which is 6. Anything to the 0th power is 1. 1 times 2 is just 2. And then the last one, 1/3 to the first is 1/3 times 2 makes it 2/3. So let's graph this. At -1, I'm at 6. At 0, I'm at 2. And at 1, I'm at 2/3. So you can see this one, like we said, is the decay graph. It goes down. So a couple of things I'd like to just note really quick. This A value, this initial value up front, if you look right here, my A was 3/2, my y-intercept was 3/2. My A here was 2, my y-intercept was 2. So that helps me find my y-intercept as long as I haven't moved too much. And then we'll talk about more transformations shortly, or even maybe on the next page. If we look at these graphs, my range started here and went up, and my domain goes left and right forever. So on the next page. Okay, so let's just recap what we've done. So make it a little bit smaller. If my B is between 0 and 1, we know it's a decay. Try it one more time. If the B is greater than 1, it's a growth. And I just want to rewrite the formula up here real quick. I'm going to rewrite this formula as f of x equals a b x minus h plus k. So if my x is positive, my x up top is positive, then there's no change. But if I make x negative, then it reflected across the y-axis. If you make x negative, you reflect across the y-axis. If a is positive, there's no change. But if we make a negative, which is like making all the y's negative, then we reflect across the x-axis. If the exponent says x plus h, if it says plus, you're moving to the left h units. And if it says minus, you're moving to the right h units. If the k at the end is a plus k, then you go up k units. And if it's a minus k at the end, then you go down, down k units. And a little note right here. This k is going to help you find, it's linked to your asymptote, which we'll talk about more. Oops. So let's make some more graphs quick. Okay, so let's use that table and do these examples. So I need to write an exponential decay with a base of 0.8. So I'm going to write that model, that f of x equals a b x minus h plus k model. So they told me my base is 0.8. If I want to reflect over the y, that means your x has to be a negative. A vertical, that's an up and down. Vertical shift 3 units down. That means this has to be a minus 3 because I'm going down 3. And a horizontal shift of 2 units left. So I want to have a plus 2 in here. Okay, so let's piece this all together, and we have to follow PEMDAS. So when I write this, I'm going to have f of x. They don't give me an initial amount, so 0.8. Now this is the trick. In the power, put a negative because you are going to reflect it, and then put the x plus 2 because you want to go to the left 2, and then minus 3. If you want to distribute that negative in the exponent, you can. 0.8 negative x minus 2 minus 3. When you pull this negative back out, you will see that you really end up going to the left. What is the domain and range of the function? So let's go back. if I'm going to go left and right forever, then my domain is going to be negative infinity to infinity, which is all real numbers. My range, however, let's look at what happened. This is a decay graph because my base is 0.8, so I did something like this. Now let's look at what happened. What happened was I reflected this graph over the y-axis because you PEMDAS, so you have to reflect before you shift. And then I went left and down, so I'm going to look something like this, just approximately. So my range is going to start here and go up. Well, that here place is that -3 because that's what I moved down. So my range is going to be -3 to infinity. And you don't touch it. There's actually what's called an asymptote, a dotted line here. So we put a parenthesis, not a bracket. Okay, let's walk through these transformations on the next one. So the negative out front is going to cause a reflection. Reflect across the y stuff is negative, so you reflect across the x axis. You have a 0.1 initial amount. Our base is 3, which means I'm going to be a growth. The +2 means I went left 2, and this -5 means I went down 5. Okay, again, what would the domain and range be? So my domain, now be very careful. We can do this. My domain is going to be negative infinity to infinity. My range, let's see what happened. Let's just go through these steps. So it was a growth graph, so it looks like this. And then I reflected it across the x-axis. So now I'm going down instead of going up. And then after I reflected it, I went left and down like this. So now I'm starting at my asymptote, which is that thing on the end right here, the -5, and I'm going down. So my range is going to be, remember I'm going down, negative infinity up to that asymptote, which is -5. Okay, let's make some graphs. Let's find all these pieces and make a graph happen. So I like to make a table and start with some intercepts and some ordered pairs. This right here is my asymptote. So my asymptote, and because it's a horizontal asymptote, things that are horizontal are y equals. So my horizontal asymptote is going to be y equals -2. Let's find the x-intercept. To find an x-intercept, the y equals 0, and to find the y-intercept, the x equals 0. So let's do this. Let's start with the y-intercept. So I'm going to get y equals 4, a -0 is 0, so 0 minus 3 minus 2. Okay, well, let's see. That's going to be 4 to the -3rd minus 2. That's going to be 1 over 4 to the 3rd minus 2, which we can type in a calculator. 1 over 4 to the 3rd. 4 to the 3rd is 1. 4 times 4 is 16 times 4 is 64. So 1/64 minus 2. That's going to equal -127 over 64. All I did was I changed this into 128 over 64 because that's 2. So it's not quite -2. So my y-intercept is 0, -127 over 64. My x-intercept. Okay, before I can make that x-intercept happen, let me just move this really quick. There's my y-intercept work over there. Okay, x-intercept. So for my x-intercept, I let y be 0. So 0 equals 4 to the negative x minus 3 minus 2. I'm going to add the 2 over, so 2 equals 4 to the negative x minus 3. I'm going to apply some tricky-ish algebra skills. So 2 equals, I'm not changing anything. I can rewrite 4 as 2 squared. That's still that 4 that I had before. Negative x minus 3 is the power. Now, at the beginning of this video, we reviewed exponent rules because I can multiply these exponents together. So I get 2 equals 2 to the negative 2x minus 6. Remember, we could distribute that 2 to everything. This 2 right here is like a 2 to the first. So for this to be equal, 2 to some magic power will equal 2 to another magical power if and only if those two powers equal each other, meaning 1 equals negative 2x minus 6. So I'm going to add that 6 over and get 7 equals negative 2x. X is going to equal negative 7 halves, or negative 3.5. So let's write that down. My x-intercept is going to be negative 3.5, comma 0. I'm going to shrink this work also. Oopsies. Try again. Oh. Okay, it won't let me shrink that work. Let's add some hash marks or some scale on the graph so we can graph what we know. Oh, try that again. Okay, so first I'm going to graph my asymptote. Y equals a horizontal line. At negative 2, asymptotes are dotted lines that you don't touch, you get really close to. My x-intercept is negative 3.5. My y-intercept is almost negative 2. If you need to plug something in, plug another ordered pair or another point in, and you can absolutely get another dot. But I'm going to get close to this asymptote and never touch it, like that. So there's my graph. My domain is negative infinity to infinity. And my range is going to be negative 2 to infinity because I started at negative 2 and get bigger. On this one, all of these tangent lines are negative slopes, so this graph is decreasing. Let's try it again. So I'm going to rewrite it first to make my life a little bit easier. This is the same thing as negative 2.5 x plus 3 plus 1. So you can see that asymptote at the end is going to be y equals 1. Let's find some intercepts. So let's do my y-intercept first. You let x equal 0. So y is going to equal negative 2 times 0.5 to the third, because 0 plus 3 is 3, plus 1. So this is going to get you negative 2 times, I'm going to write this like this, 1/2 cubed plus 1 equals, this is going to be negative 2 times 1/8 plus 1 equals negative 2 over 8, because I just multiply those together, plus 1. This is negative 1/4. Negative 1/4 plus 1 is 3/4, or 0.75, so my y-intercept is 0, 0.75. To do my x-intercept, we'll see how this one goes this time. I'm going to plug a 0 in for the y, so I'm going to minus my 1 over equals, don't drop your negative, negative 2.5 x plus 3. Divide by this negative, so I get 1/2 equals, I'm going to rewrite my 0.5 as 1/2 x plus 3. And now I'm going to use that property that we used in the last problem. The power right here on this 1/2 is 1, and the power on my other 1/2 is this x plus 3. The only way, because my bases are the same, that this can be a true statement is if 1 equals x plus 3. So we know that x has to equal -2. So my x-intercept is -2, 0. Add your hash marks. Graph my asymptote first of y equals 1 right there. And let's see. My x-intercept is -2. My y-intercept is 0.75. So you guys can see that I'm going to be coming up this way and closer and closer. My domain is -infinity to infinity. My range is -infinity up to that 1. And we didn't talk about this in the last problem, so let's talk about this one. It says, is the graph increasing or decreasing? So the best and easiest way I can tell you to figure this out is draw little tangent lines. And tangent lines are little lines that touch once, like this. And these little tangent lines, you need to say, determine, are these positive slopes or negative slopes? Well, all of those slopes are positive, so that means my graph is increasing. Okay, there's some practice problems for you guys to do of graphing, but I wanted to do one of these in particular. This one is the other way around. It wants me to write the equation of the graph. So let's label some key things. So first of all, there's a y-intercept. Second of all, I definitely have an asymptote right here. So remember, I need that y equals a b x minus h plus k. This a thing is found from my y-intercept, which is 3. So I know that is going to be a y equals 3, b x minus h. Now that k is my asymptote, so it's a plus 2. Unless it says that it's been shifted, we can make a case that it has not been shifted, because I can't prove that it has been, but I can take another point. Any other point, that's a pretty one right there. Or maybe this one, but I'm gonna use that one right there because it's a lot easier. The scale down here and the bottom is 1. So this ordered pair right here is 3, that's backwards. That ordered pair right there is 1, 3. So I can plug that 1, 3 in. So y equals 3 to find my base. B to the x plus 2. So if I plug this in for my x and my y, I get 3 equals 3 b to the first plus 2. So I'm going to subtract the 2 over and get 1 equals 3 times b. So b must equal 1/3. So my equation is y equals 3 1/3 x plus 2. So exponentials are a fancy form of compound interest. Compound interest frequently uses the formula that's on the screen right here. So let's go through what each piece means. The P is your principal or your initial amount. The R is the rate. Make sure you change your rate from percentage to a decimal. N is the number of times compounded. And T is the time in years. So let's go over some vocabulary just so that we can be successful. Annually, the N would be 1. It's compounded 1 time per year. Semi-annually, the N would be 2 times per year. Quarterly is 4. Monthly is 12. Bi-monthly means every other month. So it would be 6. Weekly is 52. There's 52 weeks in a year. And daily is 365. So make sure you know those terms. So the interest is a charge that you pay for borrowing money. If a bank is letting you borrow their money, you're really investing money in them and they're charging you money to borrow their money. The compound interest that we're talking about down here means that it's just not compounded once per year. It's compounded multiple times over the year. So we're going to use the formula, and down here, make sure that you, again, know what all these individual variables stand for. We're going to use this formula to calculate. So let's try that. So on the example, it says $800 is deposited in an account that pays 9% annual interest. So now instead of you having to pay the interest, the bank's paying you. They are investing money in you because you let them borrow your money. So my principal is the 800. My rate, it says 9, but we have to make that a decimal. So remember, if I have 9%, you have to move the decimal over twice to make it become, or the decimal over twice to make the percentage become a decimal. So it's going to be 0.9 or 0.9. Compounded annually, so that means I'm compounded once. And it says find the balance after 4 years, so my T is 4. So I'm going to write down my formula. My amount that I have equals my principal, 1 plus the rate over n to the nt power. So I'm going to plug everything in. Amount equals, my principal was 800, 1 plus 0.01, or 0.09 over 1 to the 1 times 4 power. Since you're using a scientific calculator, I would simplify as much as possible. So I would simplify this piece and this piece first. So my amount is going to equal 800. 1 plus 0.09, because 0.09 divided by 1 is just 0.09, and 1 times 4 is 4, equals 800, 1.09 to the 4th. So if I were you guys, I would type this in my calculator first, and then multiply by the 800. And it's money, so please keep in mind that when it is money, you are going to round to 2 decimals, because we do cents in 2 decimal places. You should have got that it is $1,129.27. So let's try 2 more examples. So in this example, you've inherited an emerald ring that is appraised for $2,400 in 1960. Now it's 2010. And the appraisal value has increased 6% each year. What's the value of my ring? So my principal amount was $2,400. My rate is 0.06. It says each year, so n equals 1 because the 6% happened each year. The t, how many years have gone by? Well, from 1960 to 2000 is 40 years. And then from 2000 to 2010 is another 10 years, so 50 years. So I have my amount is going to equal 2,400, 1 plus 0.06 divided by 1 to the 1 times 50th power. And you're just going to clean it up. 2,400, 1.06 to the 50th. And you're going to type that in your calculator. You should get that your amount that your ring is now worth is $44,208.40. Not a bad investment. Okay, the next problem is a little bit different. It talks about radioactive material. It says it's used to diagnose brain, thyroid, liver, and kidney diseases. The radioactive material has a half-life. So let's talk about this word. Half-life of 6 hours. A half-life is the amount of time it takes for half of my material to go away. So if it says that I start with 200 milligrams. So this is half-life 0. So no time has gone by. Half-life 0. 200 milligrams. How much substance will be left after 6 hours? So 6 hours, which is 1 half life, the amount is going to half. So I now have 100 milligrams. How much will be left after 12 hours? So now this is 12 hours. It's going to half again. This means 2 half-lives have gone by. So I should have 50. How much will be left after 1 day? Okay, so let's keep going. So to get to 24 hours, which is 1 day, I have to go to 18 first. 18 hours, which is 3 half-lives. And that's going to get me to 25 milligrams. And then to get my 24 hours, which is 4 half-life, it's going to be 12. And we'll discuss this later, but the generic formula for half-life is Y equals A, your initial amount. The base is always a half because it's a half-life. And then it's time over the half-life time. Okay, last formula. This is a special kind of compound interest because it says compounded, keyword right here, continuously. So anytime you're doing a compound interest problem and you see the words compounding continuously, that means that we're going to use this formula. So P is still my initial amount. E is a constant. It's like pi. Pi is 3.14. E is 2.7182. It's just another constant. R is still my rate, and T is my time in years. So let's try this. Terry's deposited $100 that he gets for his 5th birthday in a savings account that compounds continuously at 5%. Keyword continuously. Today is his 21st birthday. How much money will he have to withdraw? So my ending amount is going to equal my principal, which is my 100. E, the rate is 0.05, and that T is how many years. So if it was his 5th birthday and now it's his 16th birthday, 21st birthday, that was 16 years. So again, because you're using a scientific calculator, I would simplify as much as possible first. So do that 0.05 times the 16. So this is going to be the same thing as 100 e to the 0.8. So in your calculator, you do e to the 0.8 first, and then multiply that times that 100. And you should get that right now he has $222.55. Okay, so let's do the next one. Suppose that you have $1,500 at an annual interest rate of 0.95% to compound continuously. How much will you have in the account after 5 years and after 25 years? So A equals my 1,500. E 0.0955, and then same thing, two problems. A equals 1,500, E 0.095 times 25. So let's go ahead and figure out those amounts. This piece right here is the same thing as 0.475. So you should get that for the first one after 5 years, you have $2,412.02. For the other one, this right here is the same thing as 2.375. And you should get that you have $16,126.50. Okay, this is the property we were using earlier that I promised you we'd talk more about, and now we're going to talk more about it. So it's called the one-to-one property. For the one-to-one property, as long as A is bigger than 0 and A can equal 1, if A to the X equals A to the Y, this is only true if and only if. That's a big math statement. If and only if x equals y. So these two things are equal, but the bases are different. So rewrite the 9 as a base 3. Don't mathematically change anything. 3 squared is still 9. So now my bases are the same. And if this is going to be a true statement, then 2 has to equal x plus 1. So that means subtract the 1 over, x equals 1. And you can check it by plugging it in. Same idea on the other side. These bases are not the same. This one we have to rewrite both bases, and you can't change anything. So the base they have in common is 3. So 1/3 is the same thing as 3 to the negative 1, and then negative x. You can't drop the negative x that was already there. And then 3 to the 3rd makes 27. Remember, you multiply the negative 1 and the negative x, you get 3 to the x equals 3 to the 3rd. And this one's really easy. X just equals 3. So it's a cool little property you can use to solve these exponential equations.